Now that we've got an understanding of floating point numbers, now that we've got the idea of generalizing guess and check methods to do things that can do approximations, to find solutions to things, we can really start building some pretty powerful programs. We've already seen something that searches for cube roots of numbers, even if they're not a perfect cube, square roots of numbers, even if they're not a perfect square. And we've seen how we can get to quick solutions very nicely using things like bisection search, have great accuracy and still find good answers. I want to show you one last example just to give you a sense of the power of computation we can now do. I'm going to stick with the idea of finding roots of things, but show you how you can actually capture things very dramatically. And that's to use a technique called Newton-Raphson. It was discovered by Sir Isaac Newton 3 or 4 centuries ago, also discovered by Raphson at about the same time. And here's the basic idea behind Newton-Raphson. It's a general approximation algorithm that's going to let us find roots of any polynomial in one variable. So that could be, for example, the polynomial like this. I've got p of x is some coefficient times x to the n plus some other coefficient times x to the n plus minus 1 and so on. And what I want to do is find the value r such that p of r is equal to 0. It's called a root. It basically is the root of this equation. Newton-Raphson will apply to any polynomial. I'm going to show you an example of using it to find square roots. And you can say, well, I already did that with bisection search. You're right. But it's a nice way of looking at how we can generalize the computation. So in particular, if I want to find the square root of 24, I'm going to use the polynomial x squared equals 24. Because if I can find the value of x for which this is 0, then x is, in fact, the square root of 24. What Newton showed was that if g is a good guess to that root, then you can get an even better guess by taking g and subtracting from it the polynomial evaluated at g divided by the derivative of the polynomial evaluated at g. And if you haven't done calculus and you don't know what a derivative is, don't worry. We're going to show you what it is in this simple case of a square root. But I want to let you see the power of doing Newton-Raphson. So Newton showed if I got a good guess, I can make it better by taking p of g divided by the derivative of p at g and subtracting that off of g. So in the simple case, if I've got an equation that is some constant times x squared plus another constant, then the first derivative of c times x squared is just 2cx. So in my case of looking for square roots, x squared is plus k is the thing I'm trying to find a solution of, the derivative is just 2x. And so Newton-Raphson says, given a guess for the root, take the polynomial at that point, which is g squared minus k, take the derivative of that point, which is just 2g, take that ratio and subtract it off from g. Cool. We ought to be able to build that, and we can. It's a nice, tight, little iterative loop. So here's a nice way of generating the guesses. Again, I'm going to have some epsilon that's going to let me decide how close I am to an answer. I got the thing I'm going to look for, and my initial guess I'm just going to pick as that value divided by 2. And then here's the loop. As long as guess squared minus y, the absolute value of that is too big, I'm going to keep going. And as before, I'm going to count the number of guesses to see how long it takes. Each time around, I'm going to use that little equation from Newton-Raphson. I'm going to take g squared minus y, divide it by 2 times g, or guess, subtract that off of guess, and go back around. That's just the thing I did before. And I'm going to run through that loop until I get something close enough, and then I'm going to jump out. So let's see what happens if we do it. I've got the code over here. I'm going to load it in and run it. And in 4 guesses, it got a good solution. 4. Okay, it's a whole lot better than 30,000, which is where we started. With the bisection search, it was about 15 or 20. Now I've got it down to 4. Let's pick another example. Let's take my favorite example here of 54. Same thing, and I run it. And in 5 guesses, it gives me a good solution out. This is really cool. I know you don't believe it, but it really is cool because it lets me not only find cube roots and square roots, it lets me find the solution to any equation very quickly. So what we've now seen is that this idea of a guess and check method builds on reusing the same code over and over again. It takes the idea of a looping mechanism and adds to it, building into it different ways to generate the guesses and then checking to see whether I'm close enough or I want to keep going. And we've already seen now simple exhaustive enumeration, bisection search, which cuts down the amount of expense dramatically, and now, at least for root finding, Newton-Raphson, which improves it even more formally. So you've already seen 3 different classes of algorithms, and you've got a lot of tools for doing numerical computation. We're going to come back to that as we move on through the course.